On. We are on hour 34 of 36 of our class, and today we will comb braids, and I still owe you a correction for the last bit of the proof of unique factorization, and I will pay my debt either on Monday or on the last class, but I still owe you, I'm aware of that. Very briefly, what we did last time, we said, so there is an exact sequence from pure braids on n strands to braids on n strands to the symmetric group with n elements, on of n things, so with n factorial elements, really it's kind of tautological. I mean, PBN was defined to be the kernel of sigma, so this map is so this is an exact sequence by automatically, and it means that studying braids and pure braids is more or less the same thing if you know how to separate braids, and if you know how to separate pure braids, you're more or less in the same place, and by the end of the hour we will know how to do it. And it's not a split exact sequence. And then we did a little aside on split exact sequences, and I want to review it briefly. So we said, if we have, because we will use it in a moment in a slightly different context, so if we have a sequence A goes to B goes to C of groups via maps I and P, we say that it is split if there is a map S going from C to B, such that C to B and back to C, namely S followed by P, is the identity map. And in such case, we have shown that B is equal to A times C. We haven't shown, but it's kind of tautological, it's trivial, that A intersect C is 1. So A intersect C is 1 because when I say A, I really mean I of A. When I say C, I really mean S of C. But if you have something which comes from both the right and from the left, then its image on the right would be trivial because you've gone 2 steps on an exact sequence, and on the other hand it will be what you started from on the right, because S followed by P is the identity. So what you started from on the right must have been 1. So then its image here must be 1. So we are just with 1. Okay, so A intersect C is 1. And finally, A is normal in B. And hence, since C lives inside B, it means that C acts on A by conjugation. And having these 3 properties, and last time I forgot to mention this one, but still having these 3 properties means that B is the semi-direct product of A and C, and semi-direct products are relatively easy to study, so are relatively easy to understand. So that was the review of last time, and I wanted to say a little bit more about it, or not more about it, continue the discussion. So there is an obvious map from PBN to PBN minus 1, and I forgot to give the map a name. Let's call it D, and D stands for drop strand number n. Okay, so if you have a map with n strands, you can just forget the last strand, and you got a map with, if you have a braid with n strands, you can just forget the last strand, and you have a braid with n minus 1 strands. So it's clearly onto, because if you have a braid with n minus 1 strands, you can add a trivial nth strand, and you got a braid with n strands. In fact, not only I've shown you that this is onto, I've actually constructed a splitting S. Okay? But now if I want to complete it to a exact sequence, I need to tell you what is the kernel. So what is the kernel of this map? Okay? So suppose I have a braid on n minus 1 strands. Here it is. So here n is equal to 3, so n minus 1 is equal to 2. And suppose I have a third strand going around it somehow. Well, I mean, I made it trivial, but so what? Okay? And suppose this, oh, sorry, I've drawn something wrong. I want the kernel of the map. Sorry. Sorry, I wanted the kernel. So suppose I have a braid which becomes trivial upon dropping the last strand. Okay? Then in that case you could well, it will become trivial only if I drop the last strand, but I could still trivialize it. I could motion it to the trivial braid while keeping the last strand, while pushing the last strand around as necessary, right? If I so you know, now this is the wrong picture. I mean, so maybe this is a more correct picture, and you know what? Maybe instead of fixing this picture again and again, let me draw a better picture. So here is a braid which becomes trivial upon dropping the last strand. So the last strand would say, we'll do something non-trivial, but the braid becomes trivial if you drop the last one, right? So, oh, you know, I could have made it even better. I'm sorry, I maybe should have prepared a picture in advance, but anyway. Okay, so this braid becomes trivial upon dropping the last strand, which means that I can, well, but I can trivialize it. I can make the first two strands look completely straight by moving them and pushing green around. Just think of green as being made from some flexible material, so I can push it around. Okay? So really, such a braid is equivalent to a braid in which the first two strands are completely straight, and the last strand does something non-trivial between them. I think in our case it's doing this. Okay? But this means that the last strand is a point. So if you think of it as a movie of points moving, or as a movie of points moving in the plane, then the last strand moves in the complement, in the plane in which you have removed 2 points, So this is really an element of pi1 of the plane minus, so the disk minus n minus 1 points. Okay? But pi1, but the disk minus n minus 1 points, so if you have a disk and you remove, I don't know, a number of points, this is, pi1 of that is the free group. This is homotopy equivalent to, or you can contract it to to a skeleton which looks like this, and so pi1 of it is just a free group. So the kernel here is the free group on n minus 1 letters, and we have an exact sequence like this. Now, I already told you that this sequence splits. Okay? So it means that this is a semi-direct product of this with that. Okay? So the conclusion is that PBN is a semi-direct product of PBN minus 1 with Fn minus 1. Now, but now I can use induction. But you see, if I'm about to use induction, I may as well start with, I should first figure out where it will end. Okay? So what is PB1? So a pure braid on one strand is just a straight line. There is nothing you can do. So it's the group 1. And in fact, maybe I'll look one up from that. So what is PB2? So PB2, if you only have 2 strands, you can either twist them n times, that's the only thing you can do, so you get Zn. Alternatively, you can use exactly the same argument and you'll find that this is PB1, which is trivial, semi-direct product, the free group on one letter, but the free group on one letter is Z, so this whole thing is Z. Okay? Anyway, now I know where to stop. So, so now I can do the induction. So this is PBN minus n minus 2 semi-direct product Fn minus 2, all of this semi-direct product Fn minus 1. And now I can continue, and when I continue I will eventually get F1 semi-direct product F2 semi-direct product F3 semi-direct product all the way up to Fn minus 1. So I have not made it, well, I actually have made it algorithmic. You can turn everything that I said into an algorithm, but I mean, I haven't made it explicit. I haven't made the algorithm explicit, but everything here is algorithmic. So in principle, if you have 2 braids, it's very easy to decide if they are the same or not. All you have to do is to write both of them as members of this group, and in this group figuring out equality is trivial. Okay? Because set theoretically, this group is simply the cross product of all of the groups appearing here. So it's a cross product of free groups, and a cross product of free group, and deciding equality in a free group is trivial. If the words are equal, the elements are equal. If they're not equal, I mean, other than trivial cancellations, I mean, of a thing with its inverse, but I mean, if the words are equal, they're equal, otherwise they're not equal. So deciding if two braids are equal is in principle trivial. So, okay, next I want to actually have a geometric image of this. Okay, what does this look like? So, maybe I should start by having a geometric image of this. So what does this look like? Okay? So the claim here is that every braid with n strands can be written. So you see, when you have a semi-direct product, it means that you can write anything on the left as something from here times something from here. It's not a cross product, but still you can write anything here as something from here times something from here. Now, so every braid on n strands can be written as a braid on n-1 strands, followed by, so you know, pictorially, if you have a braid on n strands, you should be able to write it as a braid on, you know what, let's make n4. You should be able to write it as a braid on n-1 strands, well, regarded as an element of PBN. So I mean, I have to apply what I called the splitting to map it from Pn-1 to Pn, but the splitting just adds a trivial strand on the right, so you should be able to write it as this times, well, times in the braid group is really vertical stacking. You stack things on top of each other. So instead of writing the times on the right, I'll write it on top. So times Fn-1. How is a free group, how is an element of a free group a braid? It's a braid by letting strand number n wander around the other strands. Okay? So the claim is that every braid on, or not the claim, the content of what we have shown is that every braid on n strands can be written as a braid on n-1 strands followed by a motion of the last strand among the first n-1. Okay? By the way, how would you explain it to your non-mathematician aunt, friend, whatever? Okay? So, just take this braid with n strands, make the first n-1 strands out of metal wire, so they can't move. Okay? And so the first n-1 are solid, and the last one, make it out of some light materials that moves easily, basically a string of an ordinary string. Okay? So this ordinary string moves among the metal wire pieces over here. And now blow wind, so put a fan and blow wind coming from below to the top. And then the metal wires will remain in place, and strand number n will fly. Well, there is nothing to stop it because all of those strands are always heading up. So if they're sufficiently greased, there is nothing to stop it from sliding all the way to the top until it slides to the very top of this braid, and then it just looks like that. So actually, pictorially, it completely makes sense. Okay? But anyway, now I can continue. So if I look at this picture, right at this, then what I'm really saying is that every braid on, let's do 4, so every braid on 4 strands can be written as a product of 3 steps, where in the, so here is the separation, where in the first step you have an element of the free group on one, sorry, what? Yeah, a braid on 4 strands is a product of 3 steps, right, sorry, in the first step you have an element of the free group on one generator, which really just means Z, which really just means the first 2 strands wrap around each other. So on the first step you see a number of twists. I wrote only one, but there could be any number, and then the remaining 2 strands are fixed. In the second step, the third strand wraps around the first 2, so the first 2 will remain fixed, but the third one will wrap around them in some way and then come back to place. And then in the third step, the last strand will wrap around the first 3 strands. Okay? So this is called combing the braid. I'm not sure why. I mean, that's not what combing does. Well, it's maybe it is. I mean, maybe you could visualize this by saying is that you pass a comb through the braid and then the last strand gets pulled to the top, except if you actually try to pass a comb with straight tines through a braid of metal strings, the tines will break. So I'm not sure it's such a great analogy. Okay? Anyway, okay, so that's an algorithm to separate braids. And I have to tell you that it's a pretty miserable algorithm, because you can check that it's actually exponential time. So when you pass a relatively simple thing through a braid with n-1 strand, it comes out on the other side very, very, very twisted, and you can check that it can have an exponential number of twists in it. So in fact, it's an exponential time algorithm. There are also polynomial times algorithm to compare braids, and in fact, I think it's even quadratic. So there are even quadratic time algorithms to compare braids, but they're much harder to describe. So we're not going there. Okay? That's all I had to say about combing braids. Any questions? Any comments? Okay. So I want to tell you, so I want to start, I said we will talk about braids and variants of braids. So I want to talk about a few variants of braids. And two. And the first one is kind of lovely. So let me rederive the braid group for you. You know what? Maybe let me remind you first that we have a presentation for Bn, and the presentation was, well, last time I called the generators sigma I, but today I want to reserve sigma I for something else. So I'll call the generators gamma I. So I goes from 1 to n minus 1, and modulo relations, and the relations were gamma I, gamma j is gamma j, gamma I, if I minus j is greater than 1. This is sort of silly. And the interesting relation is gamma I plus 1, gamma I is equal to gamma I plus 1, gamma I plus 1. Anyway, that was my mood when I was defining Bn. I could have had another mood, and I could have had given you a different presentation. So here is the other presentation. So what I'll do is I'll say the following. Let me draw a braid. How about this one? So the way I will indicate a braid is I will label the strands 1, 2, 3, okay? And then at each crossing I will say which strand crosses over which other strand, okay? So this braid will be sigma, so the generators will now be sigma ij, and sigma ij means I goes over j with a positive crossing, and sigma ij inverse will be same thing with a negative crossing. So this will be 1 goes over 2, and this is a positive crossing, so this is sigma 1, 2. Then the second crossing is this one, this is 1 goes over 3, so sigma 1, 3. Again, the crossing is positive, and then the last one is 2 goes over, so sigma 2, 3, and again, in this case, all crossings are positive. So you are led to the presentation, so Bn would be sigma ij, generated by generator sigma ij. The only property is I is not equal to j. Well, sorry, both of them run from 1 to n. Okay? And then there are relations. So the top relation came from if you have like this relation here, if you have two crossings that are far away from each other, you can vertically switch their order. So this is equal to that. What am I doing? Yeah. So in the old presentation, this was gamma I, gamma j is equal to gamma j, gamma I. In the new presentation, I will say there are 4 strands here, I, j, k, and l. Also here, I, j, k, and l. And the condition here is sigma ij sigma kl is equal to sigma kl sigma ij whenever these are all distinct. Okay? So if the cardinality of the set ijkl is equal to 4. I don't know how to write if they're all distinct in a more compact way. And let me make more space. Actually, let me make more space also above. So then there is the other relation, this relation. So this relation was Reidemeister 3. So fortunately, I have the left-hand side of Reidemeister 3 already here. So all I need to do is to write the right-hand side. So the right-hand side is this. No. Sorry. You know, I should learn how to draw Reidemeister 3 quickly. Right? This is Reidemeister 3. But this is, so let's see, if this is again 1, 2, 3, then this is sigma 2, 3, sigma 1, 3, sigma, the last one is 1 goes over 2, so sigma 1, 2. Now, by the way, it's kind of easy to remember. I hope it's easy to remember. So the two sides are just, one is the transpose of the other, or the so basically you read this one backwards and you get this one. Okay? But of course, I wrote it with strands 1, 2, and 3, but it could have been any 3 strands. So the relation could be sigma ij, sigma ik, sigma jk is equal to sigma jk, sigma ik, sigma ij, provided all 3 are different from each other. So ijk is a set of size 3. And this is the end of the presentation. Am I a genius or an idiot? Well, it turns out I'm an idiot. This is not a presentation of the braid group. As stated, it does not make sense to label, so to keep the names of the strands and use them as a reference for which one crosses over. Because you see, if I cut this braid right here, okay, what I see on the top, how do I know, by just looking at what I see at the top, whether the strand here is number 1 or 2 or 3? That would depend on what I see on the bottom. So the name for the top half is not, you don't just name the top half by what it is, you name it by what it is, but you also need information on what happened on the bottom for the name to make sense. So, I mean, this is complete nonsense, the whole last 10 minutes. It's complete nonsense. Okay? But you get a fun group, nevertheless. So, let's give this group a name, and let's call this, let's call this group, so this is by definition PvBN, and later I will tell you how it is significant. So PvBN is pure virtual braids on n strands. Okay? And again, the way to get the presentation of PvBN is to incorrectly get a presentation for Bn. Okay. And then the last group I want to talk about is PwBN, and it is defined to be PvBN modulo an additional relation, and the additional relation is that sigma ij sigma ik is equal to sigma ik sigma j, sorry, sigma ik sigma ij. So I just commuted the two things, again under the provision that I, j, and k are all distinct. Okay? And this relation, well, there are better reasons for the names, but basically I is the overside. So this is something, so the name is, and you see, so if I goes over j, and then I goes over k, that commutes with I goes over k, and then I goes over j. So the name for this relation is over crossings commute, or in short OC. And you can ask, what does the W stands for? So it stands for, well, first of all, it's the next letter after V. Second, it stands for weakly virtual, and there is a reason behind this name too. It stands for welded, and that's historically welded. It's that historically the origin of the name, but I'm not sure I like it. And it also stands for warm-up, because studying PwBN is a warm-up for studying PvBN, and PvBN is maybe more interesting. Okay. Anyway, having said all of this, let me try to tell you what is, let's interpret this group. So I want to interpret this group and then go back and interpret that one. What does it mean? Okay? And I'm kind of stupid because I was going to prepare stuff in advance, but I forgot to do it. So, I'll have to do it right now. So, you see, the pure braids, the pure braid group on n strands, also sometimes called the pure, the pure usual braid group on n strands is really the motion group of n points in R2. So basically you have n points in R2 and you track how they move, and that gives you a braid. But you see, equally well, you could be looking at the motion group of n rings. You know what a ring is, right? Here is a ring. Okay? In R3, so the picture is I don't know, you have a chunk of R3, and in it you have n flying rings, so it's also called the group of flying rings. And it turns out that flying rings is a little too much, though the difference is very small, so I will restrict my attention to horizontal. Horizontal. So here it's an horizontal flying rings. So you have a number. Now you have to look at the video, sorry, at the video feed, not at the screen share. Okay? So you have n rings in R3 and they are flying around. Okay? So suppose you have 2 rings in R3 and you're asking yourself, how can they trade places? Right? Sort of the key point here was for 2 points to trade places. That was the generator. So you can ask yourself, how can 2 rings trade places? It turns out that there is a non-interesting way and an interesting way. The non-interesting way is, well, they trade places. Okay, so it's not interesting because there are, well, if they trade places by orange flying over green, or orange flying under green, or orange flying behind green, or orange flying ahead of green, all of those are homotopic to each other. Right? Because, well, I mean, I need a few more hands to show the homotopy, but basically, I think you can check it. So, so there is only one way to trade place with this in mind, okay? But there is a more interesting way to trade place, and this is one ring can fly through another, and then they've traded places. And in fact, there are 2 ways this can happen, because either green flies through orange, or orange flies through green. So I said that they are horizontal. I didn't say that they are of fixed radius. So, you know, for orange to fly through, for green to fly through orange, orange first has to expand a little bit, and then green can fly through it. And then orange can shrink a little bit, and then it can fly through green back again. Okay? Now, there is a different way to say that trading places externally is silly. Okay? And the way to say it is to say that the space of embeddings, or the placements of rings in R3 in which they are all external to each other, is simply connected. So if all rings if none of them is allowed to be kind of inside the convex hull of the other, like this, if there is no ring is in the plane of another and inside it, then the space of such rings is simply connected. Okay? So, maybe I should go back again to the motion of points. When we talked about motion of points, I should have told you when you talk about pi1, you always should specify what is the base point. Okay? The base point here is the rings are ordered in a certain order. Sorry, not the rings, now it's points. They're ordered in a certain order, 1, 2, 3. And, well, either you insist that 1, 2, 3 will be some fixed position in the complex planes, like the numbers 1, 2, and 3. Or you say 1, 2, and 3 should be in order along a horizontal line, and it doesn't really matter where along this horizontal line they are. So really you're not computing pi1 relative to a base point, but relative to a base space. And it's the space in which 1, 2, and 3 are horizontal, and it doesn't really matter where they're placed. Okay? Now, in general, you can replace base point with base space, provided the base space is simply connected. Okay? So in general, you can talk about pi1 of a space relative to a subset, provided this subset is simply connected. Whenever you have a simply connected subset, you can make it a generalized base point. If you want to relate it with the old notion of fundamental group, the relation is that if this is X and this is the simply connected base space, and now you want to compare it with the ordinary notion of fundamental group, so you choose a base point inside the base space. And now if you have a loop that doesn't quite close, you can turn it into a closed loop by adding lines into the base point. If you have a loop that doesn't quite close but that starts and ends in the base space, so starts and ends in A, then you can turn it into a closed loop by choosing lines into the base point, and it doesn't matter which lines you choose because A is simply connected. Okay, so after all this introduction, I will say that I will redefine, so PwBN, I didn't yet tell you that it's PwBN. I should say, let's look at pi1 of horizontal flying rings, and I can choose any simply connected base point. My simply connected base space will be they are external to each other. Okay? And now I claim, so this is now a claim, this is PwBN, presented before using generators and relations. So, oh my god, I spent so much time talking about it that we're barely reaching the tofu. So, I should just tell you how is sigma ij interpreted. So sigma ij is, well, I is the bigger ring, so J flies through I in the positive direction, and since I really want to run, I will not tell you what the positive direction is right now, but I will tell you next time. But I encourage you to buy another set of hands so that you can hold 3 rings at the same time, and then test all the relations. Okay? So all the relations have a meaning. They mean, a Reidemeister move will mean this flies through that, and then, blue flies through green, then orange flies through green, then orange flies through blue. And that's the same as, so you can check that all of these, that these two motions are homotopic, and the homotopy you know what? It's something to check. And finally, you can check that, the overcrossings commute becomes the relation that if you have one big ring and 2 small ones, then this one flies first and this one flies second is the same as the other way around, which really means that they could fly together. Okay? Hopefully I'll show pictures next time, because now we're out of time, so I'll stop here, but see you on Monday. Okay? And I still owe you an interpretation of V, the V group as well. Okay. Questions, comments before I disconnect the video?
About the usage of the word pure here. Because before when we did the pure braid group, it was the idea was it was the braid group,
right?
The subset of the braid group that has trivial underlying permutation.
Right.
I don't see why our presentation here has anything to like forcing the underlying permutation.
So we will talk about it next time. So there is a non-pure version, and the reason for ordinary braids, the pure version is the less fun version, and the impure version is the one that comes up more naturally. And for V and W, the pure version is the one that comes up first, and then the impure version can be constructed out of it. So we will do it next time.
And on a related note, when we say here that PwBN is pi1 of horizontal rings relative to the subspace consisting of all configurations where they're external to each other, do we have to fix that subspace of external to each other? Do we fix a particular ordering of inclusion?
No.
Like we had to fix an ordering on the line?
No. All of them are no.
Because I'm trying to understand how that's simply connected. I can see if you fix an ordering that you have to have 1 inside 2, inside 3, inside 4. Then any 2 configurations in that are connected.
No, external to each other, I mean exactly the opposite of what you said.
Oh.
I mean not nested.
Okay, got it.
Okay, they are away from each other. Okay, none is inside any other.
All right.
So they're all like that. Okay?
Makes sense.
Okay. So I will, I'll have to say more next time. Okay, so see you hopefully on Monday.